So this is just a general sort of summary to make sure that you're sort of feeling reasonably comfortable with these ideas about diffraction and double slit experiments and gratings and so on. So this is the starting point then, which is that you quite often see diagrams like these, and it's important to sort of make sure that you understand what this is telling you. So the idea is that we've got a wave that's coming this way, and instead of just progressing along a line, on this side it's what we call a plane wave. And what that means is that all of the points along this pink line are at a crest, and all of the points along this black line are at a trough. It could be the other way around, but let's say it's that way around. And what that means is that if we take any line like this one, or this one, any line along there going in that direction, the direction of propagation, then if you looked at it in cross-section, so if you looked, you know, here you're like looking down on top of the plane, but if you looked at it from the side, what you would see would be a wave where it's going from peak to trough, to peak to trough, to peak to trough, to peak, and so on. Okay, so that's what these things are representing, and therefore that is one wavelength in this case, because it's the distance from peak to peak or trough to trough. Okay, so we've got this plane wave coming in here, and it hits this wall, and there is just a small gap. Aperture is the word they tend to use, which just means a gap in the wall. And then we get this phenomenon called diffraction. And diffraction just means that when a wave passes through a small aperture, it spreads out. And what that means is that instead of the wave just propagating in this direction, it then propagates in all directions, like this, around the semicircle like that. So if we took any line from there, say to there, or to there, or to there, the wave would still look like that. And in the case of, if this was an infinitesimal point, then the amplitude would be the same in all directions. However, where things start to get more complicated is that, of course, in reality, though the aperture has a size, and that creates complications because waves emanating from one side of the aperture will be behaving slightly differently from ones coming through the middle, and they'll be behaving slightly differently from ones over that side, and you basically get interference between the waves emanating from different points within the aperture. And the consequence of that is that the intensity of the waves around all these angles is not the same. And that's what leads to this idea of an intensity distribution, which you need to know about. So you don't need to be able to explain the sort of underlying maths of this, but the effect of that is that if we define this angle as 0 degrees, and this is, you know, if you like, minus 90 degrees, and this is plus 90 degrees if it's coming this way. And you plot a graph of that angle, which we'll call theta, and this is 0 and this is plus 90 or minus 90. You get some kind of behaviour that looks qualitatively like this. Okay, so what you find is that the greatest intensity, the greatest amplitude of the waves is going to come in some kind of central peak here. So in other words, the intensity is going to be mainly focused just in some segment, some sector of this semicircle, and how wide that sector is depends on the size of that slit relative to the wavelength. Okay, because the narrower that slit is relative to the wavelength of the light, the wider that peak will be. In other words, the more of the light will effectively be diffracted over a range, the narrower that slit is. Now in real life, if we're talking about visible light, we're talking about light of the order of, say, 500 nanometers would be a typical sort of wavelength. So that's 5 times 10 to the minus 7 meters. And if that slit were, say, 0.1 millimeters, that would be about 10 to the minus 4 meters. That might be a sort of reasonable sort of slit width. And you can see that the slit is much bigger than the actual wavelength. And the consequence of that is that this peak is really quite narrow, so that actually the range of where there's intense diffracted radiation is quite narrow here. If you could make smaller slits, then you would spread it out more. But you need to be aware of this pattern. This is what you get from a single slit, and that's going to be important when it comes to the double slit experiment. Okay, so now we got the same situation. Wave coming in this way and now passing through two apertures here. And from each aperture we get this diffraction effect that the wave spreads out like that. And you can see that obviously the two diffraction patterns overlap, and you know that the principle of superposition states that when two waves meet, the displacement at any point is just given by the sum of the displacement from each of the individual waves. In other words, we get interference, so that in some places, here for example, if we look at this point there, you can see that we've got a trough in the wave spreading out from this point, and we've also got a trough in the wave spreading out from this point, because it's black in both cases. So at that point we've got trough superimposed on trough, so we're going to get a deeper trough. So that's constructive interference occurring at this point. But if we look at this point, we've got trough here superimposed on a crest there, and so if they're at the same intensity, they will completely cancel each other out. If they weren't at the same intensity, they would partially cancel each other out, and that's destructive interference. So what you can see in this pattern is that we get some places where there's constructive interference and some places where there's destructive interference. Now if we look at the pattern of those things, if we have a look along the midline here, so this is the point midway between the two slits, is about there. And if we look along the perpendicular line from that midline, then what you can see approximately, and it's only approximate because my drawing is terrible. If I'd been able to draw more accurate waves, this would have been exactly correct. But you can see more or less that along that line you always get constructive interference, because black overlaps black, so troughs overlap, crests overlap, troughs overlap, crests overlap, and so on. So along that line you always get constructive interference, and that means that if we put a screen over here somewhere, so if we put a screen here, then along that line the light arriving there will have a big amplitude. Okay, the wave's going to have a big amplitude due to constructive interference. And that will give you a bright area on the screen. Now if we look at other angles, we can see that along certain lines you always get destructive interference. So for example, you can see that along a line that sort of goes roughly like that. Oops. Let's get the black one here. Oops, messed that up a bit there, but you can see we've got crest overlapping trough, crest overlapping trough, crest overlapping trough, and you know they're slightly displaced, but that's just my drawing. That's not really, but you can see that these points of overlap lie roughly along that line there, and that means that if that line continues to the screen, we'll have had destructive interference all the way along there. So you get a small amplitude, and in a perfect case it would be 0. So it would be completely dark because you'd have completely destructive interference. So small amplitude due to destructive interference. So in other words, it's going to be dark along that line. And in between it's going to fade basically, because you're going to get a transition from constructive to destructive in between. So you won't just get sharp lines, you'll get a sort of graduate fading from constructive to destructive, if you like, and therefore you'll get fringes of brightness and darkness along there. So we're going to get the same thing at the corresponding angle going in this direction. What you're going to get are equally spaced dark, bright, dark. And if we go out again, you can see that along that line, like that, you're going to get constructive interference again, and along the same corresponding line here, you've got constructive again going there. So we're going to get another bright fringe out here and out here, and if you drew it accurately you would find that you would get regularly spaced bright and dark fringes. So that's the basis of what's going on in the double slit experiment. But superimposed on that, remember that these are not all going to be of equal intensity because of what we saw, which was that the intensity of the diffraction from each slit tends to be focused primarily in front over a certain range, and then there'll be only limited intensity in some peripheral regions, and that's going to affect the intensity distribution of the fringes that you get on the screen. Okay, so this, remember, is the kind of intensity distribution that you get from a single slit of finite width, okay, as a result of the sort of interference you get from light coming from different points within the slit. So this is the single slit of finite width distribution, and what happens then is that that distribution is superimposed on the fringes that you get from the double slit experiment. So again, if you had infinitely narrow slits, the fringes would all be equally bright, you know, going out to all angles, but they're not, because it's superimposed on this distribution. So what you'll tend to get is a sort of intensity distribution that looks kind of like this, maybe. So in red is what you see from the double slit experiment then, and so this and this and this and this and so on, these would be the bright fringes. And obviously where the intensity is low, those would be the dark fringes. So you get an intensity distribution then, and you don't have to draw the whole thing, but what you expect to see then is that you get an intensity distribution that looks sort of like this for the double slit. So you get a bright fringe in the middle and then less bright as you move out there. And if you go out to even wider angles, you get these sort of subsidiary maxima where there is again, there are places where you get a central brighter fringe again, and then smaller ones around it, and the same here and here. But they're much less bright than this central one. So often we just focus on that central peak when we look at these double slit patterns. So just returning to this pattern a little bit, it's also interesting to look at what the relationship is between successive points along this line where you get the constructive interference. So at that point you can see that effectively the wave has travelled one wavelength in all directions around this semicircle here. So the wave that's coming from this point has been diffracted around that semicircle there, so it's travelled essentially one wavelength from there. And the same is true here, because this is the semicircle of light diffracted from that point, and again you can see it's travelled half and then one wavelength from there. So those 2 points, the light has had the same path length to reach there. And if we go to the next point where we have the 2 peaks like that, then you can see that to reach that point you've gone a half, one and a half, 2 wavelengths to reach that point on this semicircle being diffracted from here, and on the one being diffracted from here you've gone 1 wavelength there, 1.5 and 2 wavelengths on this one. So at that point both of the diffracted waves have travelled 2 wavelengths, and you can see how it's going to work. That's going to be 3 wavelengths and so on. So these have equal path lengths. But if we look at these ones, then this point here, to reach that point from this aperture, you can see the points on that semicircle have travelled 1 wavelength, but the ones on this semicircle have travelled 2 wavelengths. Okay, because there's the 1 wavelength semicircle, here's the 2 wavelength semicircle. So at that point they've travelled 2 wavelengths from there, but only 1 wavelength from here. And that's always going to be the case when we get to this point. This is on sorry, where are we? So if we're looking at this point here, so here's the semicircle that's scattered from, that's diffracted from this point, and you can see that it's basically travelled 1 wavelength to reach that semicircle, 2 wavelengths to reach this one. So it's travelled 2 wavelengths from there, but from this one it's travelled 1, 2, 3. Okay, so it's the 3rd pink line out, so it's travelled 3 wavelengths to reach that point. So the path lengths differ by 1 wavelength there, and the same would obviously be true here, that the path lengths differ by lambda at that point. So that's an important relationship, that you get this path length difference which differs by a whole number of wavelengths, because you can see the next line where you get a run of constructive interference, which is going to be sort of up here, they're going to differ by 2 wavelengths and so on. So it's got to be a whole number of wavelengths different between the two. So that's an important idea which feeds into the calculations that we come on to. The other thing we need to talk about is the idea of coherence. So the definition of coherence is that the 2 sources produce waves which have a constant phase difference. So in this case you can see that if, for example, we compare light that's going straight through, not being bent, coming out from this aperture and from this aperture, the two sources are exactly in phase, right? Because where you have a trough here, you have a trough there, and where you have a peak here, you have a peak there. So along that line and along that line, the waves are exactly in phase, and that will always be true for for parallel waves coming from the two sources. But that's just the way it's convenient to draw it. It doesn't have to be the case that there's zero phase difference between them. It just has to be a constant phase difference in order to get a pattern of fringes. So it's worth just looking at what happens, for example, if the two sources produce waves that are antiphase when you compare them coming straight through like that. So let's just have a quick look at that. So in this case we've got two sources where, if you compare light coming straight through in that direction and straight through in that direction, you can see it's antiphase, because where you've got a peak here, you've got a trough there, and where you've got a trough here, you've got a peak there, along that line and along that line. So it's a constant phase difference because it remains antiphase all the way along that line, and again the same would be true for any pair of parallel lines coming from the two sources. So it's constant phase difference. But if we look at what that does to the diffraction pattern, you can see, so if we do this midpoint line as we did before and just look along the line there like that, so remember that was where we got our central bright fringe when we had the two sources that were completely in phase, and now you can see that we have destructive interference all the way along that line. So that means that when you get to the screen here, you're going to get a dark fringe in the middle. But if we just look at a bit of an angle again, you can see that sort of along there you've got constructive, 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 constructive. So you're going to get constructive interference along that line, so you're going to get a bright fringe centred on there. And so on. So you're going to get the same pattern of alternating dark and bright fringes, but it's going to be shifted. So that's why when we talk about coherence, we don't say that they necessarily have to be in phase, because so long as you have a constant phase difference, you'll still get a pattern of fringes, but it will be shifted relative to the one we looked at originally.